Okay, so in the last video, we talked about the causes of ringing. And in particular, we found that the various circuit techniques that we might use to most efficiently deliver voltage from the output of one device to the input of another are the same techniques that are going to give us some pretty severe ringing. And those are very damaging to any digital circuitry or any digital electronics. So we could use some ideas of how we reduce that. And we're going to aim for something called a match. A match means that we're going to somehow kill or eliminate these reflections, these back and forths, these ping pong games, and try to get things to settle out faster or maybe even instantaneously so that we no longer have this problem. So first we're going to talk about two techniques, and we're going to build up complexity and sort of build up the quality or the value of these techniques one after the other. All right, so you could sit and you could brainstorm ideas, and maybe some have already occurred to you, but let me just rebuild the simple circuit right here. Here's a transmission line. Here's the load resistor. All right. And let's put some numbers to this. Okay, let's say this is 1 volt, and this is 5 ohms internal resistance, and let's say this is 2,000 ohm, and this is 50 ohms for the transmission line impedance. All right, now this example actually worked out in the notes. I did not go through it in the last video, but the example is in the notes, so you can see that this will produce some very severe and long-lasting ringing that we'd like to get rid of. So one of the quickest and easiest things we might do is called a perfect match. And so to do that, I'm going to make a little hole right here, and I'm going to add a 45 ohm resistor on the source side. And on the load side, I'm going to add another resistor in parallel to this 2,000 ohm resistor, and it's going to have a value of 51.3 ohms. All right, the reason I chose 51.3 is if you go through the math, the parallel combination of 2,000 ohms and 51.3 ohms is 50 ohms. So what we've done is a pretty seemingly clever way to make a perfect match, right? This is called a perfect match. As we're going to find out, though, it ain't so perfect. So now I've got 50 ohm as a transmission line impedance, and I've got effectively a 50 ohm load, which means that my gamma L equals 0. On the generator side, I've got a series combination of 5 and 45, and that's 50. And so I've also got a 50 ohm line running into a 50 ohm termination on the generator side. So I'm also going to have a gamma G equals 0. So this looks pretty good at first glance. We've got no reflections. And so we know we're just going to send one wave. It's going to go out to the load. It's going to stop right there, and everything else is over. There'll be absolutely no ringing. All right. Hopefully you can see right away that there's going to be a big problem. In fact, there's going to be multiple problems. All right. So let's think about the steady state for a second. What are the voltages going to be after we wait long enough for that wave to travel from one side to another? All right. So let's start with, here's our 1 volt at the generator. And in steady state, we are going to have resistor dividers between 5 ohms, 45 ohms, and this 50 ohm parallel combination right here, right? And so what that means is that the voltage here on the load is only going to end up at 0.5 volts. In a digital circuit, that's obviously extremely problematic. There's no reason to assume that the digital logic may catch that as a 1. It may interpret that as a 0. It may get very confused because it's right on the edge. We certainly don't want to push to that edge. So this is problematic on that count. The other big issue is, think about power, right? In any circuit that we're designing these days, low power is extremely important. We want to keep the power as low as we possibly can. All right, so in the original circuits, the power that we had to burn was equaled V squared over the resistance that's facing the battery, right? So the battery was 1 volt, so this is 1 squared divided by, in the original case, it was 5 plus 2,000. Right, so the total resistance facing that 1 volt was 5 ohms for the internal resistance plus 2,000 for the load. This is a pretty small number, right? What is it now after we've done this match? P equals V squared over R, which equals the same 1 squared, but now it's divided by 50 plus 50, okay? Now this is very problematic because this power right here is much bigger. So we are burning a heck of a lot more power just in order to get this match, and that is really problematic. All right, so this perfect match is not going to do the trick. Let's forget about that. All right, bad idea. So let's try a different strategy. This next one is going to be called series match. In the series match, we're basically only going to do one of those things. I'm going to keep that 5 ohms and the 45 ohms on the series side, on the generator side, but the load, I'm going to allow that to stay. And so this is 2,000 ohms. This is still 50 ohms. Here is 5 ohms, and this is 45 ohms. Okay, so here we have a match, but the match is only on one side. Right, we've got a gamma on the generator side, which equals 0, but the reflection coefficient on the load side is pretty high. Right, it's quite nearly positive 1. So we've got a one-sided match, you could say, and this is called a series match. Now, this is certainly much better than the perfect match that we described before, right? So the downside is if we inject a wave right here, let's trace what happens to it. Let's do this in blue. If we inject a wave right here, when we first close that switch, it's going to propagate down to the end. It's going to encounter a reflection coefficient. It's almost positive 1. It's going to reflect, turn around, and come back. And when it reaches the generator side again, it encounters a reflection coefficient of 0, and then it's done. So there's 1 back and forth, and then we're done. That's not going to give us long-lasting ringing. You got to wait 1 extra half, one-way delay for things to settle out, but that's not necessarily a big problem. All right, we still have a couple of issues here. Number one, we are still adding this 45 ohm resistor here, and that's still going to burn extra power that we'd like to avoid. Right? It's not nearly as severe as it was before, but it's still extra power that we don't want to waste. And again, these days with low power application being what this is, if you think about a cell phone, all right, and you've got millions and billions of these little circuits scattered throughout the integrated circuit inside the cell phone, if this elevates the power by 15%, for example, that may not sound like much, but that could be the difference between an 8-hour battery life and a 7-hour battery life. And you better believe that phone manufacturers are going to care a lot about that extra hour of battery life, and so would the people buying the phone. So even this little 45 ohm resistor is going to be problematic from the perspective of power wasting. And we're not quite getting that efficient transfer of voltage. If this is 1 volt right here, then the voltage that appears on the load will end up being 4.875 volts. You do the math. Again, a lot better than we had before. Or, I'm sorry, that's not 4.875. That's yeah, it's 0.975. Right. So again, much better than it was before, where we only got a half volt before, but still not perfect, and might be helpful to create as much of that safety margin as we can. So again, better than before, but not so good. All right, so let's go back and let's try the other approach, which is parallel match. Parallel match, we're going to put back the resistor on the parallel side, but not the source side. And we're going to use that as a baseline. So here we got 5 ohms. We're going to stick that 5 ohms and leave it right there. We're not going to have the 45 ohm resistor. So this is 5 ohms, 1 volt, 50 ohms, we're going to take that 2000 volts, sorry, 2000 ohms, and we're going to put in series with it, sorry, in parallel with it, that 51.3 ohms. Okay, this is called a parallel match. This gives us a reflection coefficient on the load side will be 0. And even though we have a reflection coefficient gamma G is about -1, that's not actually so problematic because we're never going to get a reflection coming back to the generator side, right? We're gonna, whatever voltage we place on this circuit board is gonna propagate all the way down to the end, and it's gonna stop right there. It's gonna be absorbed at the load. So that's good, but again, we have the same problems before. The load is now 50 ohms, and so it greatly increases the power draw that this battery has to supply in order to keep this voltage from the load. And just to give you a number, it's going to draw about 1,300 times more power than the case where we didn't have any matching scheme at all. And that's unacceptable for pretty much any application where power is even remotely an issue. All right, so those are a few different possible strategies. So as we can see, placing resistors around provides some sort of a benefit, but it's not the benefit that we need yet. We're going to have to turn to alternative strategies, and we will cover that in the next video.